p-square plane, which is some sequence of bound states, and then a continuum, which is represented by this branch cut. Then we're going to add a term, which I'm calling a finite volume correction, which must know about both the finite volume physics and the infinite volume physics, so these cuts. We looked at the Poisson summation formula last time to write some generic relation to illustrate this idea. If I have some function f and I look at a finite volume object in some quantum field theory, you're going to have some loops over spatial momenta. The momenta are quantized. I'm using periodic boundary conditions. And the difference between this and the infinite volume, where k is a real variable in 3 dimensions, is in general given by this, where there's some power law dependence in the volume, but you can use the Poisson summation formula to write it like this, where you have some integral over momentum with some Fourier phase and the function here. And depending on the behavior of the function, we will see that this allows us to evaluate, or at least, which in general is difficult, but we can at least illustrate that corrections for smooth functions will scale exponentially suppressed in the volume, whereas corrections for quantities that are singular have this remaining power law dependence. So today, I want to think about single particles. So look at, and Amy said this in her lecture, that if you can measure, say, the ground state energy level, you can associate that with the mass of the particle of interest. And we're going to see what the finite volume behavior is when we do this to see if we have to make any further corrections. So for single particles, I'm going to use quantum field theory in a box. The results, generally, when we think about scattering and the Lucia condition, are independent of any particular theory because everything relies on mass shell physics, which is, we had some discussions by both Sebastian and Andre where you can construct generic effective field theories, but on mass shell they have to give the same result independent of the details of the field theory. So for illustrative purposes, I'm going to consider lambda phi 4 theory as a catalyst to derive these finite volume corrections for both this case and the scattering case next time. So the Lagrange density is given by this. I note here that this m is the mass parameter. So at tree level, we usually think of that parameter as the mass. But as we've seen in the effective field theory lectures, when you start going higher order corrections, you get self-energies and things shift around. So I say here, I'll call this the mass parameter. The true mass is when the 2-point function for the propagator blows up. That's the singular point. So we'll see how to connect that to this quantity here. All right, so let's look first in infinite volume. And this was, the idea was already illustrated by Andre in a lecture. So the 2-point correlator, which I'm going to use slightly different notation from him. I'm going to call the exact 2-point correlator a line with a dot. And the Dyson expansion in terms of one particle irreducible objects, or I'm not doing that yet. This quantity here is 1 pi, and I'll give an example of that in a moment. And we can sum the series to give the Dyson equation So this is the free propagator, and then we just start dressing it with interactions. So you can show, and I'll leave this as an exercise, primarily because Andre already showed what the generic idea is. That the two-point correlation function within this field theory is something like this, where I pi squared is equal to the open bubble, where I put the lines through just to not, this is a free particle propagator. I'm just interested in the bubble part. So by the spectral theory, right over here. Which is what we did yesterday, or at least I said what the infinite volume one was. It's going to look something like this, where, let me put an I epsilon in there just to be consistent, where the pole term is associated with the fully dressed propagator, but then you have further corrections which are going to be not important when we're focused on energies near the pole. So for p squared near the physical mass squared, this extra term is just a smooth function. So all the branch cuts and stuff that are hiding inside there won't go on mass shell if I'm interested in physics near the pole mass. So this is another kind of issue that I'm saying it here, and it's going to become more important when I get to the scattering case, is when we derive these finite volume formalisms to be used in analyses, we don't want to be too ambitious and try to describe the entire energy region, because if we do so, we know we need to keep track of all the singular structure for all energy. But if we limit our energy window to something manageable that we're actually interested in, we can isolate the physics we care about, and then all the physics we don't care about is not going to be relevant for the systems we care about. So I may have been a little redundant there. So for this case here, if we're interested, let's say, let me try it over here. Let's say the p-squared plane for this particular theory was something like this. You have a single pole for the physical mass, and then a continuum of stuff that can happen if the energy was high enough to excite multi-particle production. If I limit my energy window to be here, where I'm only near the pole, the branch cuts will never come online. As Sebastian showed, you get some heaviside functions mathematically that show when these thresholds open up. So they're not going to turn on, and this is effectively smooth. So that S function contains all this other stuff here. When we go look at two-particle scattering, we will take into account two-particle scattering threshold, but then ignore, say, three-particle and higher. So now, this is not relevant for any singular structure. I compare this to this, and I find a condition for when the physical mass, to relate the physical mass to these quantum field theoretic quantities. So in perturbation theory, you calculate the self-energy to some order, and you do renormalization to determine what the physical mass is in terms of your theory parameters. Here, again, I'm using this as a catalyst to try to make a connection to the finite volume world. So let's look at the self-energy, some diagrammatic representations. So in this theory, you have one diagram that's of order lambda, and you have two diagrams that are order lambda squared, and then further diagrams at higher orders. At order lambda, so the Feynman rules for this theory are one of the simplest ones. In momentum space, those are the two Feynman rules. So this, and I'll call this momentum K. Minus I lambda integral d4k over 2 pi to the 4th I over k squared minus m squared plus I epsilon plus all the higher order stuff. So this is a loop integral that Andre is dying to do tomorrow. I'm going to partially do the integral in the sense of once I relate to the finite volume quantity, I'll do some simplifications. So note here that in principle, this integral diverges in the UV. So you, like all quantum field theories, you usually, for the most part, need a regulator to make the theory well-defined, and then you renormalize, and at the end of the day, anything physical should be independent of any regulator of your theory. I'm going to assume an implicit regulator because I don't want to make life too hard and have to deal with extra terms floating around. One of the kind of a nice one to deal with when you're dealing with these finite volume quantities is a polyvalars or polyvalars-like object. So that's where you replace the propagator with the propagator plus extra terms. So I'll write a generic version here with some coefficients that you need to determine in order to make the divergence regulate away with some large UV cutoffs that you need to take to infinity at the end. So you could do all this and then everything that will follow through should work out. One of the reasons why I won't do this is because if I look, when we write the finite volume version out, you're going to have the exact same structure in here, and it's also going to be UV divergent. So I'm going to have a UV divergence here and a UV divergence here, but they're going to cancel out. So the correction is going to be independent of this UV regulator. So that's one of the reasons why I don't want to deal with it explicitly, because it doesn't change the physics that we're after. All right, so there is the infinite volume self-energy to leading order. Let's look at the finite volume version. The finite volume Feynman rules will be the exact same there. The only difference is that four-dimensional loop integrals will become a one-dimensional integral in the energy variable because we're not in the temporal component in a box. But the spatial components will be put in a box, so they're sums. So the finite volume Cl of P will have the exact same structure as before. Where here now I write pi sub L to be the finite volume version. And loops with finite volumes, I'll write a little v inside the loop, just to help remind us that these diagrams I'm talking about are finite volume objects. So to leading order, we have this. What about relating this to the spectral component? Well, from spectral theory, P squared equals mL squared is the physical quantity that we're after. So this is, say, the ground state energy of the finite volume correlator you're calculating from lattice QCD. So say the neutron mass, but this is the neutron mass in the finite volume, not necessarily the neutron mass in the physical volume or in the infinite volume. So we need to connect that quantity there to that quantity there. So if you do that, mL squared minus m squared plus pi L mL squared equals 0. This is the relation between the spectral decomp and what we have here. So let me just emphasize mL will be the center of momentum frame energy level for the ground state, which is a function of L. So far, so good? Any concerns? So we can take the difference of the correlators to look at the finite volume correction, but we can just as easily, and if you do it that way, you'll also get this relationship. Oh, I want squares. So we're going to take the square of the finite volume mass minus the square of the infinite volume mass. Physical mass, sorry. And this is what I'll call the correction term to the mass. So using this relationship and that yellow box relationship together with the explicit expressions for the self-energies, you will find that, let me just write down the answer, that this is plus I lambda 1 over L cubed, sum over K minus the integral of the energy integral of the integrand and summand. And this assumes, I had to do a little assumption here. When you go and derive this, that the correction is small relative to the scale of the mass itself, because you get some sequence, so this is going to depend on ML, whereas that one's going to depend on mphys, so you have to assume some small correction to make it the same quantity. And again, I'm implicitly assuming regulation. So this is exactly the sum minus integral bit that I defined before, and this is the function that we're applying that to. Let's do this temporal integral. So let me write I So we can use Cauchy's theorem to solve this integral by identifying the poles, structures. So I can split up the denominator. And I'll leave you to verify this. So this is quadratic in k squared. I want to write it in terms of k naught. So k naught minus omega k plus I epsilon, k naught plus omega k minus I epsilon, where omega k is equal to the square root of m squared plus k vector squared. Let me just squeeze in the drawing up here. So in the complex k naught plane, we have one pole here, omega k minus I epsilon, one pole here, minus omega k plus I epsilon, and I'm going to choose this contour to wrap around. When I do so, apply Cauchy's theorem, I get 1 over 2 omega k. So I'll let you verify that. It's using the same Cauchy theorem that Sebastian has discussed. All right, so we're on our way. We did one integral, knocked that out. Yeah. Because when I take this difference, it's going to be something like m phys minus the self-energy of ml. So I want these two to be of the same argument. ml is related to m phys and delta ml. So if delta ml is over ml is negligible, then I can replace this by m phys. And I have to do that iteratively, but the leading order one is the only one that's going to matter for the illustration purposes, because you can just sum everything back up. Any other questions, comments? So delta ml squared is I lambda 1 over L cubed. I have the sum minus integral of now, let me double check. I got rid of that factor I already. Oh yeah, the factor I goes away from Cauchy residue. So this is 2 omega k. Yeah, just 2 omega k. So it's 1 over 2 omega k, and let me write this as 1 over 2 square root of m squared plus k squared. And again, let me remind you that there is some implicit regularization here when you do these integrals. Okay. Now, for this function here, I'm debating how much to show. Yeah, all right. So now I'm going to use the Poisson summation formula So this is I, L, integral through k over 2 pi cubed e to the I p dot n L 1 over 2 square root of m squared plus k squared. Say again? Oh, yeah, you're right, sorry. Thank you. I lambda sum of n not equal to 0. So I can think about, I wrote p here, this should be k. So this is a three-dimensional integral. This only depends on the magnitude of k. This has angular dependence. I can remove the angular dependence by performing a plane wave expansion. So if we recall, for this particular Fourier phase, something like 4 pi times the sum of L, 0 to infinity, I to the L. Then you have these notorious Bessel functions. Right. So the angular bit we can get rid of. So you have three-dimensional integral. You can write this in spherical coordinates. Like so. And the angular bit, all that's going to hit in here is this spherical harmonic. By the orthonormality, it's only going to pick out the L equals 0 guy. Okay? Because you need two spherical harmonics in the orthonormal relation, but we only have this guy here, and there's no other angular dependence. So L equals 0 is the only option, the constant case. Say again? Yeah, so there's going to be 1 over square root of pi, and we're going to kill 1 over square root of pi there. So we have something like delta ml squared, again, skipping a couple steps just for time really, is going to be something like 1 I lambda over 2 pi squared times the sum, and for L equals 0, J of 0 of n k L, I'm sorry, I wrote P again, it should be K, of nkl is equal to sine of k and L over k and L. No, capital L here, yeah. This is making mistakes all over. N, K, capital L. So K should be everywhere. Magnitude of N, magnitude of K, capital L. This is lowercase l, factor of I. Spherical harmonic, N, K. This one's starred. Yes. So prefactor, sum over n modes not equal to 0. You're going to have the integral of dk 0 to infinity, k squared over square root of m squared plus k squared sine k and l over k and l. All right, so getting a lot of special functions to play with, which is nice, but also kind of tedious. And as I go through my notes, I'm trying to argue something else, which is probably not as illustrative, but let me take a break from this for a second and do a simpler integral to illustrate it, just so I don't need to involve modified Bessel functions. So consider, maybe I should have just done this from the start, consider an integral 0 to infinity, I'll call it p this time since it's in my notes, p sine of p and l over p squared plus lambda squared. So it's almost the same thing. This NL, let me just move it out here. It's not affected. And then this k cancels out one factor of k here. So I have this expression. I'm replacing the square root by this pole term. Okay. Why? The analytic structure here is going to involve branch cuts in the imaginary k-axis, whereas for the second one here, I'm going to get two poles. So what I'm going to do is illustrate this for the simple case of two poles, and then the argument works the same for the square root, except it's going to involve not just simple exponentials, but modified Bessel functions, which in the large L limit are going to be exponentials. So it's the same result, just not wasting too much time. So this here, I'm going to do two things. One, notice that the integrand is even under p, sine is odd, p is odd, so together this thing's even, and this thing's even. So I'm going to divide by 1/2 integral from minus infinity to infinity. Okay, let me write it like this. So, then I'm going to do another thing. Sine is the imaginary part of the complex exponential. So I'm going to this is a real integrand, so I'm going to write imaginary part of e to the I p n l over p squared plus lambda squared. P. So this is my complex plane. I have a pole at I lambda and minus I lambda, since that's when p squared plus lambda squared goes to 0. I'm integrating along this line. I can choose a contour, say this one here. It will pick up one of the poles, not the other. By Cauchy's theorem, again, assuming everything is well regulated, this is going to give you pi I times e to the minus n lambda L. So this integral is going to give some factor times an exponentially suppressed mode in the mass scale of the integral with the box size. Same thing happens here, but again, it's going to involve modified Bessel functions. Do the exercise if you're familiar with them. It's not bad, you just have to assume regulation to close the contour out infinity. The mass scale here is going to be m, so what you'll find, so after some math, the thing we're actually after is going to go, let me get the factors correct, is going to go something like lambda over 2 times 2 pi ml to 3/2 power e to the minus ml plus order e minus square root of 2 ml. So this is the n equals 1 mode. This is n equals square root of n squared equals 2. So the magnitude, we're not including the 0 mode, so you have n squared is 1, n squared is 2, so on and so forth. So the leading order term is going to be some prefactor times some exponential suppression in the mass times the box size. And you're going to get higher order ones, but this is going to be the leading order. So again, same thing as I did here, just a more complicated function because that's square root. And in general, let me kind of write down our first big result. Let me just do it over here. Yeah.
Minus 1 over 2w, or no?
In the, say again? Yeah.
1 over 2w. It means it's missing minus, or no?
I don't think so. I think it's a plus. Yeah, I'm taking my contour in the negative direction, which is going to be opposite sense of the usual Cauchy way, or what is usually written with the Cauchy theorem. So it's minus 2 pi I. So the mass correction is exponentially suppressed in terms of the mass. So delta ml goes like e to the minus m physical L. So if this were a pion, in QCD, the lightest mass scale of the theory is the pion mass. So any hadron is going to, the mass corrections from the finite volume are going to scale as the lowest mass scale of your theory, which is going to be the pion. Yeah. Mm-hmm. If you, depending on what you're after, you may want to keep track of more terms. Here I'm looking at the leading order scaling relation. So in practice, a lot of calculations in spectroscopy want to choose, so in QCD spectroscopy, you want to choose m pi L sufficiently large, so m pi L about 4 gives you about 1% correction. So depending on what you're doing, you may need more terms if you want, to control different types of precision, or to control your precision of the quantity you're after. But this is, as a rough estimate, something to think about. That way the scaling corrections here are going to be in order 1% and not relevant for the stuff we're going to be after with scattering. But again, if you're after different quantities, maybe you need more stuff or more terms. All right. Any immediate questions or concerns before I start motivating the two-particle case in the last 15 minutes? Yeah. As a screening mass? I'm not too sure in what sense you mean. Yeah, I mean, yeah, in that sense, if you are looking at large L limit, this thing's going to vanish exponentially and be irrelevant. So but it becomes more important the smaller the mass scale times the box size are in this sense. So does that make sense? You have a comment on this? Do you want the microphone? Yeah. Maybe you have a better understanding.
I was just thinking, actually, yeah, so you can think of it as you have this periodic boundary conditions, which you can reinterpret as an infinite copy of your lattice, right? And so in that sense, it's like you have a pion in the universe you care about, but it has pions around it, which is sort of like screening. Right? You have an infinite cloud of pions that go off to infinity that modify the mass. So I think, yeah, it has a very similar, but I think I used to at least think of it more as just like in E&M when you do images, like if you put a charge near an electric plate and you can solve the problem by doing the method of images, it's kind of like that.
Thank you. All right, so in the remaining minutes, I want to start discussing the two-hadron case, or two-particle case, and what we need to set up. Well, okay, before I do that, let me kind of summarize what we're seeing here. So I realize I haven't done that yet. So you get this exponentially suppressed correction, and if we looked at kind of the integrand we have to deal with here, sure there's a square root singularity, but it's often the complex plane. If we think about just the real axis where the sum and integral is happening, this quantity doesn't vanish, right? So there's no singular structure here. So in effect, the sum and integrand is smooth for the summation and integration bounds. So the takeaway, and you can prove this rigorously in Luciar's first paper on finite volume physics, he goes through arguments using arguments about smoothness for the current for the integrands or summands to prove this. I did it by an explicit example. You find, now state it like this. That if your function that is in the correction, so within the integrand or summand, is smooth, meaning there's no possible way for singularities to be hit, so meaning there's no on-shell propagation of particles, that's the physics sense, then the finite volume correction, you can always play these same tricks and write it as some order exponential to minus the mass scale, the lattice mass scale of the theory, which for QCD is pions, times the box size. So this is the key takeaway from this. So other diagrams you can consider like this for the propagator. If p squared is the mass squared of the problem, then these three particles can't go on their mass shell, which means the correction they're going to give is going to be order exponential to minus ml. Okay? There. For the two-particle case, it will be different. You can maybe already guess why. It's because when we do two-particle physics, we are interested in scattering, so when two particles are propagating along. And we already saw from these phase space integrals from Sebastian that once you have, two particles propagating, you get square root branch cuts. Square roots in the physical integration region are going to lead to these singularities that are going to spoil this. So let's look at non-interacting two particles. So I can think about in my correlator, I can make an operator O of x that is something like some amplitude that connects two, let me write it more explicitly. So here's an example. To create a local two-particle operator, we will integrate over these dummy positions and weight them against some function with two field operators. You could do that as well, but maybe you can't do that because you need some certain certain locality properties in order to not spoil the singular structure at x. So I think if you have a product of two, you have essentially like a 1 over x squared type singular behavior, right, for small x. So that's why I'm doing this convolution type. Yeah, so this is some local function at x, which means my correlator, and I'll write free, just to remind us it's non-interacting, will be something like some, I can make this more exact by including some symmetry factors and such, but I'm being, let me be exact. So this is some symmetry factor that Sebastian introduced earlier. This is momentum space. So integral d for x, e to the I, p dot x. I have 4 of these integrals. Times the time ordering of these field operators phi. So this 4-point function is something that is usually confronted in the first course on field theory. Again, I won't go through all the details of doing the Fourier transforms and everything. We'll just write it down diagrammatically and see what we get. So this thing here will look something like yz, x plus y, x plus z, and then you'll have so these are the three topologies we have for this 4-point function. So I can write a what I'll call generalized Feynman rule. So CL of P, when I take this and convolute it with these two local functions, it will look something like this. All right, so these two vertices will be integrated together as with these two, same with these two, and then these will form together. So this disconnected bit comes from here, and I get two diagrams here that are going to come from here. Those two diagrams are going to cancel out one of these symmetry factors. And then this open bubble is what I mean by generalized, in the sense that it's going to wrap up whatever I use to create the operators. It's going to just wrapped up in there, all right? So some local vertex that I constructed. So this thing will look like the symmetry factor 1 over L cubed, sum on K, integral over the momentum or the temporal bit, and then the Fourier transforms of these two, which I'm going to write in terms of K and P. So one of these particles here is going to carry K. The other one will carry P minus K, the total momentum being P. And then I'll call because one of these is creation, one of these is annihilation. So for free particles, we only have these two sets of diagrams. This one I'm not going to consider any longer, because if we think about what we just did before, in terms of the momentum, which is flowing this way, can I have these two particles go on their mass shell? The answer is no, because these are essentially disconnected vacuum bubbles. So there's no way that this particle and this particle can go on mass shell simultaneously in terms of this momentum. So I can never have this, the corresponding expression for the propagators of these two. I'll have one of K prime, let's say. They'll never hit their mass shell in terms of P. This one, however, there is a possibility for some given P that K squared will equal M squared and P minus K squared will equal M squared. That's going to give some new interesting physics when you actually have on-shell particle propagation. So this one will lead to finite volume corrections that are going to scale exponentially, which I'm going to ignore. Okay? So I should stop here. So next time, what we'll do is I'll rewrite this again, and just, we have two particle correlator for free particles. We'll write the corresponding infinite volume amplitude. take the difference and see what kind of corrections we get. I claim that because we have a possibility of 2 singular structures going on mass shell, we're going to get corrections that scale as a power in the volume. And anything that becomes smooth when we do our manipulations, like these 2 terms here, will just be exponentially suppressed. And I'm going to assume we're working with a box size large enough that ML is going to give negligible corrections. Okay? So next time we'll continue with this and then make them interact. Okay, thank you.
Questions? Everything was clear.
Good. Or everyone's tired. Because I think we are, so.
Well, if there are no questions, I think we can call it a day and go home.
Yeah. All right, thank you.